Hello. Today I'm going to talk about how to find the feasible space given that there are multiple computationally expensive constraints. A bit of motivation. We were talking to some building designers and they were tweaking many parameters and components before finalizing their design. They had to make sure that all these design exploration that they were doing, they were producing designs that met certain constraints. So for example, they wanted to make sure that the overall energy consumption of the building did not go beyond a particular threshold. So the issue there was that to find out whether the energy consumption stayed below a particular threshold, they had to run a computational simulation, and they were expensive. They took a few minutes before they could tell whether a design was feasible or not. So clearly, the slow feasibility determination hampered the overall design efficiency. So here we want to help them by making this process really quick. So we want to make sure that they can quickly tell whether design is feasible or not. So here is the general problem at hand. So we have L constraints that define a feasible space where each of these G1 to GL functions should be below T1 to TL. And the challenges here are, again, there are no analytical models for these constraints, so we have to resort to running some computational simulations, which are expensive. So we really can't afford to look at many different designs, okay? So to enable that, the solution that we are proposing here is that we are going to build a binary classifier that can rapidly determine feasibility once trained. But for training it, of course, because there is a limited budget on how many evaluations we can do, we are going to adopt an active learning approach. Okay, so let's start with seeing and understanding how regression for classification work. Okay, so here we are given a function g of I x, and this is shown with the solid blue line, and it has a threshold ti, which is just above 0. So we have to make sure that we can determine the feasible space, which is these light blue regions where the function response goes below t of I. What we are going to do now is we are going to build a Gaussian process model for this gi of x. And Gaussian processes are a form of Bayesian modeling technique, and we'll see how useful they can be in this context. Of course, we don't have access to all these data points, so what we do, we take and select a few x's where we are going to run this gi of x expensively. And once we have that data set, we train a Gaussian process model. The beauty of it is that it has produced a mean prediction, which is shown in solid blue here, and it also tells us how uncertain it is about the mean prediction. And it turns out for Gaussian processes, the predictive distribution is actually normally distributed with a precise mean and standard deviation as defined by the whole mechanism. So this allows us to compute some probabilistic queries about the whole domain given the predictions. So for example, we can ask what is the probability that a solution response is below this threshold Ti, which is essentially the volume that lies below, volume of predictive distribution that lies below this blue line. And it's shown in red here. So with this probability of feasibility calculation, we can immediately tell where the feasible space is given these predictions. All we have to do is say, okay, when the probability of feasibility is greater than 0.5, that means the probability of feasibility is greater than probability of infeasibility, we are in the feasible space. And this feasible space is shown in light red here. So clearly we have already identified that there is a feasible space here, and it is a close approximation of the left region. However, the right region has been ignored by the model. This is particularly due to the high uncertainty level here. But of course, the estimation is not good enough in this instance. So what we need really is to select more data points so that we can train this regression model and improve the classification and accuracy in these two regions. So for active learning, what we are going to do, we are going to take a Bayesian search framework and use it for our purpose. Okay, Bayesian search is quite popular in optimization. The core idea is that we train a GP model for each of the constrained GI, and then we define an acquisition function, which is a measure of utility, that maximizing which is going to tell us where we should sample next. By sampling, I mean expensively evaluate that particular proposition. And once we have evaluated that X star, we increase our training data set, we add that to our training data set, we train our model again, so long we have the budget on the number of evaluations remaining and we don't exhaust it. Once we are finished going through this loop, we will then return all models so that we can rapidly classify for any tentative X, whether that is feasible or not. And in this particular paper, we developed a new acquisition function. So let's have a look at the development of the acquisition function for a single constraint. So when we are designing acquisition function, we typically try and strike a balance between exploration and exploitation. In the context of classifier, what we really want, we want to identify solutions along the boundary of feasible and infeasible spaces. So exploitation in this context is essentially wherever the probability of being at the boundary is high, we should sample there. On the other hand, of course, our models are poor approximations when we begin, so the uncertainty in predictions should be large. So the entropy of the predictive distribution actually tells us how uncertain or how much information can we gain from sampling there. So that's our exploration term. So let's have a quick look how they look when we plot them. So this magenta line is showing us the probability of being at the boundary. So the probability of being at the boundary is computed from the probability of feasibility and the probability of infeasibility. If we take the product of them, it tells us what is the probability that we are at the boundary. And we can clearly see that wherever this red region is, the probability of being at the boundary is quite high at the edges of that red region. So now let's have a look at the exploration term. It turns out the entropy of the predictive distribution is actually maximizing that is actually the same as maximizing the uncertainty in the predictive distribution. So this is shown with orange here, and we see wherever the uncertainty is quite large, this is high. So we are just going to take a product of exploration and exploitation, and that produces this green response here. And we are going to maximize that, and it turns out that when X is just below 0, it is maximized. Okay, so the idea is that we are going to sample there. So let's sample there. It just changes the predictions once we have retrained our model, and essentially it's now telling us that we should sample here. We will take a sample there, but let's have a quick look what happens if we didn't consider the uncertainty and only exploit it. If we only exploited, then we would have sampled around here. So that would have improved our estimation of this region, but not this region. So let's sample that one, let's sample another one here. And now let's have a quick look what happens if we only use exploration term. If we only use exploration term, in this instance, we see that we should be sampling somewhere in the middle of the right region, but the product or the acquisition function that we have is actually telling us to sample somewhere near the boundary. So we are actually striking a good balance between the exploration and the exploitation terms. So after we have taken about, in total, 10 samples, our estimation of both the regions is pretty good. And this is what we wanted. We can just give this classifier to our building designers, and they can then immediately rapidly tell which is whether a design is feasible or not. So of course we are interested in multiple constraints. In the literature, people have summed over all constituent acquisition functions, or they have considered the maximum predictive value and used that to select which acquisition function should be used. But we propose something different. We notice that the predictive distributions for multiple models is a multivariate Gaussian distribution. So for example, if we had two models, G1 and G2, this is what it produces. And now we also note that exploration and exploitation terms are integration problems, multidimensional integration problems. And if we assume independence between these models, we can analytically compute these exploration and exploitation terms for multiple constraints. And with that, we can come up with our acquisition function and use that in estimating the feasible space. So here we show on the left for x0 and x1, two variable decision space. The feasible space is shown in light green, and the dark color is showing the infeasible space. And we started out with two crosses as initial samples, and then sampled these dots, and finally produced a probability of feasibility. And it seems that we have a very good approximation of the true feasible space on the right. So we tried several test problems and several other potential competitive alternative acquisition functions. And what we saw that our proposed method actually outperformed in 3 out of 5 problems. So next, we are going to investigate the efficacy of this in constraint optimization. Thank you for listening.